Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, good morning, everybody. Thank you for joining us. We're very fortunate to have Professor Rob Johnson visiting us here. I know him from when he was a grad student back at Berkeley. I think at the very first conference I went to, I was trying to save money, and he had a spare bed in the room he was renting for the conference. And so he looked out for me when I was a very young grad student, so I'm very happy to have him here. I'm familiar with his work in the security world, where he's done some very cool stuff on sort of language-based security, looking for vulnerabilities in the Linux kernel. But lately he's been looking at optimized data structures, particularly for high-performance systems, and in this case, file systems. So, Rob?
Thanks, Brian. So, good morning, and thanks for having me here. And this is a talk based on BetrFS, which is a project that has a lot of authors from a lot of different institutions. If you don't, I'm not going to actually name everybody, but it's a collaboration between Stony Brook, which is where I'm from now. Tokutech Incorporated is a startup by some of my co-authors, Rutgers, and MIT. And this was a talk, it's an expanded version of a talk from FAST this year, USENIX FAST. And my goal here is to actually communicate information. So feel free to ask me questions and stop me at any time, because I really want to hopefully teach you about what write-optimized data structures are if you don't already know them, and how they can impact, or how they can benefit file system design, but also how they impact file system and system design, because they're kind of a radical departure from the data structures that we're used to. So let me begin by explaining the motivation. If you take an off-the-shelf file system, something like ext4, which is kind of the default file system in most Linux installations, and you run a benchmark where you just do a gigabyte of sequential writes, and you run it on a spinning magnetic disk, and the disk is rated for 125 megabytes per second, then you'll see that ext4 gets a throughput of about 104 megabytes per second. And so for a sequential write load, ext4 does great. It's getting most of the disk bandwidth out of the disk. On the other hand, if you do a random write workload, same file system, same disk, but you're doing small random writes over a 1 gigabyte file, then the throughput that ext4 gets is only about 1.5 megabytes per second. So it's hardly getting any of the performance out of the disk. It's really wasting a lot of the potential performance. That little sliver is what it's actually getting. Now, so what's going on here? And you've probably guessed the real problem is that these random writes induce a lot of seeks by the disk. And if we do kind of a back of the envelope calculation, the average seek time on a disk is around 10 or 11 milliseconds. And the OS is writing data at 4 kilobyte granularity, so there's about 1 seek for every 4 kilobytes. And so if you work that out, that would imply about a half a megabyte of bandwidth for random writes like this. Now, we did a little bit better, but we weren't seeking over the entire disk. We were seeking over a 1 gigabyte file. And presumably, Linux did a little bit of I/O scheduling to try to get things in some rough order. So it's not surprising we did a little bit better.
And the disk does, too.
And the disk might have done some more. Or
The disk definitely.
OK, the disk definitely did some.
You did a confirmation time, too, right? You lose another few milliseconds for
Yeah.
so it's even worse.
Yeah, yeah. So, but still, this is a problem if you're doing random seeks for every I/O. There are other file systems that try to overcome this. So the most well-known class of file systems is log-structured file systems. And what they do is whenever you write new data, they just append it to a log. And so appending to a log doesn't require any seeks, and so you can write data really, really fast. The problem is that over time, as you write to a file in different locations of a file, the file gets kind of scattered over the disk, and it's not stored in any meaningful order on disk. And so when you go to read back the file, then you have to do all those seeks, and it can be very slow. So log structured file systems they have a different performance trade-off, but they still represent a trade-off between these two types of operations, random writes and sequential reads. Now, what BetrFS does is it uses a new class of data structure called WriteOptimized Indices. And WriteOptimized Indices, they can take in data at a very high rate, so they're not really seek-bound, they're more bandwidth-bound. But they do maintain logical locality. So things that are logically consecutive are stored more or less physically consecutively on the disk. So that when you go to read them back, you can read them back very fast. And one of the main contributions of our BetrFS design was a schema for mapping file system operations down to operations that the WriteOptimized index can perform efficiently. And so that we're trying to extract as much of the performance from the WriteOptimized index as we can and carry it over to the file system. Another important thing we did was we implemented all this inside the Linux kernel rather than using Fuse or some other kind of external interface between the kernel and the file system. And as a result, we found there are some opportunities for redesigning the interaction between the file system and the rest of the kernel to get some additional performance. I'll tell you a little bit about that later. We're not the first to do a file system based on a WriteOptimized index. There have been several others that have shown that write optimization can be used to speed up some operations in file systems. Our goal really is to take things as far as we can. So to try to take this write optimization to its logical conclusion in file system design to see how much we can get done. Also, this prior work was all in user space. And as I mentioned, we want to understand how write optimization affects the system design and the design of the higher level file system. So we wanted to do things in the kernel. All right, that's the overview. I want to dive down now into what a write-optimized data structure is and how you can build one and what its performance characteristics are. And for that, I just want to introduce a simple performance model that we'll use to think about how well different data structures perform. This is called the disk access machine model. It's also sometimes called the external memory model. But it should hopefully look pretty intuitive to you. The computer has some RAM of size M, although that's not really going to come up in this talk. And then you have a disk of however big size you need. We don't really care about the size of the disk. And in order to operate on any data, it has to be brought from the disk into RAM. And data is moved in blocks of size B. And then, of course, if RAM gets full, you have to shuffle something back out to disk. You have to swap it back out. And the data size is going to be N. So if you see capital N's in the later slides, that's what it's referring to, the total number of data items. And all we care about in this model is how many block transfers we perform during some operation, like a lookup or an inserting of a new item. We don't care about computation in memory at all. So we're going to completely ignore that. We just have to set that aside, and maybe we'll come back and think about it later.
This model has all the blocks being the same size?
Yes. So this model simplifies lots of stuff. All the blocks are the same size.
So metadata and data in particular. So you're just counting seeks, really?
Yes. We're just counting seeks. And we don't care about whether two blocks are adjacent or not. We don't. Every seek is a seek. We just count seeks.
Okay.
Yeah. There's a lot of stuff that this model throws away.
Important things. Okay.
Yeah. Yeah. We're going to add back in bandwidth a little bit later in the talk.
All right.
But it's still a really helpful model for understanding performance of data structures. As a warm-up, let's look at Btrees. Who here knows Btrees already? Everyone knows Btrees. Okay. Let's do it just to make sure we've got the terminology on the same page real quick. So in a Btree, you've got nodes of size B. So every time you access a block, you're just going to read in the whole node. And the entire space of this node is used to store pointers to the children and the pivot keys that tell you which child you need to go to next. And since the fan out is B, or roughly B, the height of the tree is going to be log base B of n. And what that means is that if you want to do a query, you have to do log base B of n block transfers to get to the leaf. And if you want to do an insert of a new item, basically an insert is query for the item to get the leaf that it would go into and then put it in the leaf and then write that leaf back. So it's more or less just the same cost as a query. Good? Maybe it's even a B plus tree. I don't know. But we're not going to use them, so I wasn't too careful about it. So this data structure, by the way, okay, you guys all know this, so I'm preaching to the choir maybe, but I mean, this has been the data structure for databases for like 40 years. Yeah. And there's file systems based on this too, like BetrFS in Linux is BtRFS.
Like NTFS.
NTFS is a Btree file system?
The directories are Btrees. Okay. It's extents and Btrees.
Okay.
And that's been shipping for 20 years.
That's right. So, a very venerable data structure. But it turns out it's not the best you can do. There is, in fact, an optimal trade-off curve between the I/O cost of inserts and queries in an on-disk data structure. This was proved back in 2003. And the curve is parameterized by an epsilon. And I'm not going to ask you to read or understand this. There won't be a quiz on this part at the end of the talk. But it turns out that Btrees are basically at one end of the curve. If you kind of plug in epsilon equals 1, you get log base B of n for both operations. The point that I really care about is this one. Because if you plug in epsilon equals 1/2, then you're still going to get log base B of n for queries. What you actually get is basically log base square root of B of n. But log base square root of B is just twice log base B. And so this is still order log base B. But the big doozy is that you get a square root of B in the denominator for an insert cost. And if you think about what a typical value for B might be, it could be something like 1,000. And so the square root of B is roughly like 30. And so what this means is that you can build a data structure that can ingest data an order of magnitude or 2 orders of magnitude faster than a Btree, but its query performance is essentially the same. Yes?
Constant factors?
The constant factors, there really aren't any hidden constant factors here, except for maybe that factor of 2. The tree will be twice as high. However, I wouldn't get too hung up on that.
There's a factor of 2 in the other one also.
Yeah, well, I think there might really be an extra factor of 2 here that the other one's not paying. But what my co-authors have told me they've seen in doing their startup is when they go to customer sites, oftentimes it's not really a matter of a trade-off between the queries and the inserts in maintaining an index. For many people's workloads, the data comes in so fast that the only index they can maintain is a timestamped index. And so when it comes time to query, they have no index. And so what this makes this makes it possible to have an index at all. So it's not really a trade-off between this and this with a factor of 2 that's missing. It's this and, well, I didn't have an index. I had to scan the data. So here's a cartoony version of this trade-off curve. If inserts being slow over here and fast over here, and queries being slow versus fast, and a Btree has fast queries, but it's kind of, as far as this trade-off curve is concerned, they're kind of slow inserts. And fortunately, the shape of the curve means there's a huge opportunity for us to slide our data structure along this direction and get dramatic speedups in inserts with only a modest slowdown in queries, a very small slowdown in queries. And so that's the target of opportunity for write-optimized indexes. Questions? Everything so far so good?
Well, this is slow and fast. Slow is log slow on one axis and linear slow on the other one. So it's right. If you're just logging and you don't have an index, then point queries are linear slow.
Actually, I think technically logging is not on the range of the curve that I showed you.
Yeah.
Yeah. It's
like really bad.
Yeah. So let me show you an example of a data structure that moves along this curve to the point that we were looking at. This data structure is called a B to the epsilon tree, which is, maybe now you can guess how we got the name BetrFS. It's very similar to a B tree, but we're going to use the space in our nodes of size B differently. We're only going to allocate a small amount of that space to pivots and pointers to the children, so the fan out of the tree is going to be square root of B instead of B. And so that means that the height of the tree is going to be log square root of B instead of log B. And then what we're going to do with the rest of the space in this node is we're going to use it as a buffer for newly inserted items. So whenever we insert an item into a tree, we simply stick it in the buffer of the root of that tree. So la-di-da, I'm inserting items. This is really fast. I don't have to do any log-based B-type work. If I've got the root of the tree cached in memory, this is basically no I/O at all. I'm just adding things to the buffer. And then once the buffer fills up, I just flush all the items down to the buffers of the children. Not all the way to a leaf, just one level down. Let's think about what the cost of different operations are going to be. Does everyone understand the data structure first? So, items will always live on the path from the root to the leaf that they belong in. So we can always find an item by simply doing a normal searching algorithm. The only extra cost is going to be that we have to look inside the buffer to see maybe it hadn't gotten all the way to a leaf yet. But we're ignoring computation, so that's basically free. We don't count that. And so a query still basically takes log square root of B IOs. Just go a root to a leaf path traversal, and the height is log square root of B. Now,
so less than that usually, because you'll almost always hit one of the buffers.
Not sure. It depends on the workload. I mean, if you think about
it, it doesn't work, but you've got a lot of space in those buffers.
You do have a lot of space.
This data structure, you ought to wind up with most of the space in the buffers rather than the leaves.
I'm not sure that's...
Or like half of it anyway.
Well, let's suppose the square root of B is like 30. Then I think you'll have this space divided by 30 at this level. And then that divided by 30 again at the next level. And so I would estimate about 3% of the space.
Let's see. You would have, so the leaf would be size B, right? The row above it, so if the square root of B is 30, then B is 900.
Yeah.
Right? So that means that you've got 870 in each of the next to leaf nodes, and then 900 in the bottom. So half your space is one level up.
There's 30 times as many leaves as there are.
Yeah.
Oh, sorry. Never mind.
So I think the total space of the top of the tree, if square root of B is 30, would be like 3% of the total database size.
Right, so it doesn't matter.
Yeah, yeah. Most of your data is going to be in the leaves. Yeah.
It seems like it's making access quick to the data near the root, but isn't that data in your RAM anyway, and it doesn't need to be accessed quickly on the disk? I don't understand.
He's avoiding the writes.
We're avoiding the writes. Queries are the same. Queries, you still go all the way from root to leaf. And in fact, as you're going to see, we're going to end up going all the way to root to leaf anyway. But let's analyze. So
see, on a write, you only have to write it.
Good. Great. I really appreciate the question.
Appreciate the answer.
So let's analyze the query cost. I'm sorry, insert cost. We're going to do an amortized analysis. So the number of IOs we need to perform a flush is we need to load square root of B things. So that's square root of B IOs. We can count this one square root of B plus 1, whatever. Just call it square root of B. And then how many items do we get to move as part of this operation? Well, we move B minus square root of B. Let's just call that B, because square root of B is nothing compared to B. And so the amortized IOs required to move one item down one level is square root of B IOs divided by B things that got moved down. So it's 1 over square root of B IOs to move one thing down. And everything needs to move down that many levels. So the amortized IO cost to get everything inserted into the database is this is the amortized IO per element moved down one step. This is the number of times an element needs to move down one step. And so if you simplify as I did before, you just get log base B of n divided by the square root of B. So this data structure is super duper fast at handling inserts of new data. And lookups are basically the same as in a B-tree. Oh, OK, so I just noticed a question online. This is probably a little bit of an old question. So they asked, can I precisely define sequential write and random write with an example or a scenario? Sorry, I didn't see the question sooner. So a sequential write would be typically either something along the lines of you just call write with a 1 gigabyte buffer and say, here, write all this data to disk at the application level. Or you might do a bunch of small writes. Maybe you're writing 64 kilobytes at a time, but each 64 kilobytes is after the last 64 kilobytes in the file. A random write, you can think of it as essentially we run a random number generator that tells us the offset within the file that we want to write, and then we write maybe a byte of data or 8 bytes of data, some small amount of data to that offset in the file. Sequential writes occur all the time. You can think about like any sort of multimedia application, streaming data from a video camera or something like that. Random writes occur often in databases where data is arriving and it needs to be added to an index. OK.
So
yeah.
So this works very well if the workload is uniformly distributed over the leaps. You push square root of B down when you need to flush.
Yes.
Do you need to consider uneven scenarios?
So actually, you can get even better if you have bias. There's many slight tweaks on this data structure. I kind of gave you a pedagogically simple one, where when this gets full, you flush to all the children. You could be greedy and say, well, I'm going to figure out which of my children is going to get the most of this stuff, and I'm only going to flush to that child. You still get the same amortized cost, but what that would mean is if someone was hammering on a particular region of the database, just inserting a bunch of stuff to this leaf, that's all destined for this leaf, then this buffer would be completely full of things that were all going to the same child. And so your amortized cost would be 1 over B instead of 1 over square root of B.
So what you say is that you, in your system, you will flush in a biased way, in terms of activity level.
Then you've got to do tree rebalancing there too.
So yes, you can do bias flushing like that. In fact, one thing we've been working on, I'll get to your question. As you're going to see, our sequential I/O performance is not as good as other file systems, but it's within a pretty decent constant factor. And we're trying to speed that up. And that's sequential I/O you can think of as a very biased, I insert a bunch of stuff that's all going to the same part of the tree. So we care about that case. OK, your question was
Tree rebalancing.
Tree rebalancing. So this, in terms of maintaining the balance of the tree, think of just this as like a B-tree. Say we're going to do splits and joins of nodes. And more or less, the algorithm is exactly the same, except you kind of just have to split the buffer when you split a node. But it's obvious how to do that. And it turns out that just like in a B-tree, the actual I/O costs of, even though splitting and merging is very complex in terms of the code, in terms of I/O, it's
kind of log I/O.
it's small I/O. It's really not that important. Did you have?
Yeah. So I don't understand how we got the over the square root of b. If you look at an infinite trace, each block is going to be written to the root, and then it's going to be written to, and then eventually it'll be evicted to the next level, and eventually all the way to the leaf. So each block is going to be written in order logs over log square root of b n times. So why is the amortized cost not log base square root of b of n?
Because, good, right. So you're right, every item does get written log square root of b n times. But the reason we get to amortize that is because when we move an item from one level down to the next, we move a bunch of items.
Ah, I see.
Yeah.
Do any skip lists on top of this?
Could you do skip lists on this?
Yeah.
Let's talk offline. One more operation I want to just keep in your head is range queries. The way you implement a range query is more or less the same as in a B-tree. You do a query for the start of the range, and then you read through the leaves. You do have to keep reading through the higher levels as well to check their buffers, but the total cost ends up being log base b of n. That's the IOs to find the start of the range. And then if your range query contains k items, k over b IOs to collect all the items in your range. Yeah, but we're throwing away the. Yeah.
Well, it's just that sometimes it is and sometimes it isn't. So.
Right, we're going to fix the parameter of 1/2. Yeah. I know, I feel a little bit like I'm cheating sometimes.
Well, honestly, you probably would have done better to just skip the order of and carry the constants through all of this analysis. If this was a practice talk, that's what I'd tell you.
It's not a bad idea. Okay, so this is the B to the epsilon tree. I want to dive a little bit into range query performance and argue that we can do range queries at nearly disk bandwidth. And the reason is that we can have very large values of B. Now, what do I mean I can have very large values of B? Doesn't the disk have a block size? Disk transfers data in blocks of 512 or 496 or whatever. But an application could choose to just say, well, I'm going to always issue reads of 1 megabyte, or I'm always going to issue reads of 64 kilobytes. And if you look at these asymptotic formulas I showed you a minute ago, then it's quite obvious making B bigger reduces the number of IOs I have to perform, which is not a big surprise. If I just put my whole database in one big block, I'm great. But that is ignoring the other cost of doing a read, which is there's the seek time or setup time, and then there's transfer time. And obviously, the transfer time is going to grow with B. So there's kind of this sweet spot that you have to choose in terms of how big can be. And it's a little bit complicated by the fact that if you work out the bandwidth cost for an insert, it's square root of B times log base B. But the queries, it's B log base B. And then for range queries, it's B log base B. But what we can do is we can tweak the data structure a little bit so that the bandwidth costs on all of these scales with square root of B. Which I will, and then once we've done that, then that means that the bandwidth costs grow very slowly with B, and so we can make B really big.
What's really big to you?
Like 4 megabytes. Whereas the typical node size for a B tree is like 4 kilobytes, or some.
They use a single server is 8.
Right.
And it's ridiculously small.
Right. So some of them use like 64 kilobyte nodes, but they don't get much bigger than that. Most B tree, that's called a big leaf B tree. And so we can dramatically speed up.
Even at 4 megabytes, you're probably using a third of your time seeking.
No.
It's in 10, 15 milliseconds when you add. Anyway.
So I think if you're using 4 megabytes, then if the disk is 100 megabyte per second disk, you're going to do about 25 seeks per second. 25 seeks is about, actually you're right, yeah, about 10 milliseconds, about a quarter of a second. Oh, right, okay.
I worked this out.
Oh, you're good. So how do we get these bandwidth costs down? Essentially, we're going to organize the internals of a node a little bit differently. We're just going to put all the pivots up front. That's your pointers to the children, and the pivots, the keys that tell you which child to go to. And then we'll just arrange the buffers for each child afterwards, and each buffer will be size square root of B. This isn't going to change the asymptotics of the insert costs at all. When an insert occurs, it can do a single seek, read this whole thing, flush things down, and then write it back to disk. But what it means is that on a query, all we need to do is read the pivots and read one buffer for the contents of the stuff that's going to that child. And so this is still a constant number of IOs, and now the bandwidth is reduced to square root of B to read that node rather than B. But it doesn't affect the insert costs at all.
Something funny just happened there. So, how do you, okay, I didn't understand that, but something very strange just happened. So, when you're doing a point query, I understand you read the pivots, right? That takes you an IO. How do you know which buffers to read and why only one of them?
Good, okay. So, well, there's sort of two ways you could approach this. One would be every buffer has a fixed size. So you just know it's offset.
But then you lose the unbalanced advantage that you just told us about.
That's right. I'm having to, that baby's going out the window.
Okay.
I think we can get it all, but I'm not going to describe a data structure that gets it all in this talk.
Okay.
And so what you do is you would read a pivot. You read the collection of pivots, and that would tell you which child your query is going to be routed to. It will also tell you which of these buffers you need to look in to see if the item you're looking for is actually in the buffer of this node.
It will do that, but then the time to read the buffer at that point is not small, right?
That's right. So it's going to be 2 seeks instead of 1.
Yes, it's two seeks, and I guess these things are big enough now that they cost, well, like 2 seeks to read the whole thing,
Yeah.
right? And so you save not very much by doing that. It looks great because you're reading much less data, but you're actually saving not very much time by doing it.
Right. So I'm not going to go into the implementation that we use, but the implementation effectively does this trick at the leaves only. For the internal nodes, it doesn't really bother. And that's because most of the time the internal nodes are going to be cached. You kind of imagine that the top of the tree is cached anyway.
The top of the tree, tops of the trees are always cached.
So it's not really worth it.
Next to bottom.
Yeah. But I want to give you the intuition that we can, in terms of the asymptotics, we can get things in the right shape that enable us to support or to operate efficiently with very large node sizes. And so now, those B's turn into square root of B's. And if you compare that to a B tree, a B tree, the bandwidth costs are B. And so that's why Btrees versus B to epsilon trees have this different sweet spot in terms of node size. And so typical B tree node sizes are 4 to 64 kilobytes. I can't say there's a typical B to the epsilon tree node size because there's only one B to the epsilon tree implementation that I know of in the world. But a good one is somewhere in the range of 2 to 4 megabytes.
It's sort of funny, right? Because you're like with the B tree, claiming that 64 kilobytes is actually a good B tree node size only happens when you count the wrong thing. What you actually want to count is time.
Right.
And so like counting bytes transferred is a no one's constrained by their IO bus bandwidth. They're constrained by the seek time on the disk or the IO time on the disk.
Yeah, I'm not. I don't make a
64 kilobytes
judgment.
is a nutty size for a B tree. It's way too small.
Yeah, I'm just making a statement about what.
I believe you that is the size. But there's two things to tease out here, right? The B to the epsilon tree actually does better, and also the things that it's competing with are tuned for the computers of the 1970s, and that's really true. And so, so you get some credit for cleverness, and then your competition loses some credit for lack of cleverness.
I'll take it. But what this means is that since the nodes are really big, when we're doing a range query, essentially we're reading a big swath of data, and then we do a seek to read another 4 megabytes. So we read another 4 megabytes, and we can do those range queries at disk bandwidth, or nearly disk bandwidth. Also, okay, so there's another question that's popped up. Can you please briefly compare this tree to log-structured merge trees? Who here knows log-structured merge trees? Great. So a log structured merge tree is a very popular WriteOptimized data structure that's used in Cassandra and HBase and a bunch of other of these modern open source databases. And it is WriteOptimized. There are some versions of a log structured merge tree that have the same asymptotics as a b to the epsilon tree. Most of them actually have worse asymptotics. The query complexity in a naive LSM tree would be log squared, like log b of n times log of n. You can improve that for point queries by doing a Bloom filtery thing, and that gets it down from point queries to log base b of n. But it doesn't help with range queries. You still have a log squared because you have to do a search within each of the levels of the LSM tree. So I'm sorry if nobody else knows what LSM trees are and can follow that, but that's sort of the short version. There's another feature of a b to the epsilon tree, and this also interacts poorly with LSM trees, but it works nicely in b to the epsilon trees, which is called the upsert. So in a lot of times in a database, you've got a record in the database, you want to update it, and the normal way you would do that is read it, modify it, write it. And if you think about it, what we've just seen in a b to the epsilon tree is that the I/O complexity of a query is like log b, but the I/O complexity of inserting is log b divided by square root of b. So if every insert was tied to a query, we would basically be running at the speed of the query. We wouldn't be getting these performance gains. And so we want to avoid doing queries whenever possible. And so an upsert enables us to transform a read, modify, write operation into a blind, just insert something into the tree. Yes, great. I like the look of, I'm skeptical about this. So suppose I've got, this is maybe a banking database and I've got $5 and it's keyed by my ID and I deposit $10. So an upsert is essentially a message that gets inserted into the tree, just like any other item might be inserted into the tree. So it's just a blind, just like any other insert algorithm or operation. But an upsert message has a destination key that this is going to apply to, an operation to be performed on that key and value once you found it, and then parameters to the operation. And so this just gets serialized and placed in the tree. You can think of it as like a continuation or a saved function with some state. And this message will get flushed down the tree over time, just like any other piece of data that's been put in the tree, until it finally reaches the leaf that holds the key that it's destined for. And at that point, the database system will apply this operation with this parameter to the old value, compute the new value, and then replace the old value with the new value. And then this message can just be discarded.
And will they be ordered?
Pardon?
The order with the...
That's right. So temporal ordering? Right. So it will maintain temporal order within this buffer, but also they'll be temporarily ordered. The older upsert message will be further down the tree. Things never jump over each other in this flushing process. Now here's one of the biggest steps where we ignore the cost of computation, which is, what if this message, this upsert message, is still sitting in the buffer and I do a query for my balance? Well, what we do is we just on the fly apply the upsert message. So the query for my balance will descend the tree, get my old balance, and then it'll walk back up the tree looking for upsert messages that apply to this key and apply them and then return the current value. Now there's a question, once I've done this, should I update the leaf or something like that? And there's actually some heuristics you can use to decide, is it worth the additional I/O of going ahead and applying this back to the disk? Or maybe it's just cheaper to just throw it away and the tree remains unmodified. And so if you're querying that thing a lot, maybe it's worth going ahead and updating the value. If the queries are rare, it's not worth it. But in this model, we're just ignoring computation. So we're going to ignore the cost of that. But this lets us do read, modify, write type operations as fast as an insert. So to summarize, here's the b to the epsilon tree performance. Inserts and upserts both run in log b over square root of b time, which is super duper fast. Point queries are in log b time, which is the same as a B tree. And range queries can run in time log b plus k over b, but b is really big, so this is essentially at disk bandwidth. What is this? These are the asymptotics. What does it mean in practice? If you assume that the top of the tree is cached, then most queries are about 1, maybe 2 seeks. And then you can, if you're doing a range query, you just read at disk bandwidth. Then that means if you're running on a spinning disk, you can do hundreds of random queries per second. And then inserts and upserts, you can do tens of thousands, sometimes if your computer is good enough, hundreds of thousands of these per second.
So I just worked out the numbers.
Okay.
And the numbers say, one, if you have a, so B is 4 megabytes.
Uh-huh.
Then, and it takes you 16 bytes for a key and an offset, right? 8 bytes of, so you have 8 bytes of file address and 8 bytes of disk address and 8 bytes of logical file offset. That means that root B is 100, the branching factor is 125 times 4 megabyte entries, which means that a tree with just a root is a half a gigabyte. A tree with a root and one level under it is 62 gigabytes, and a 3-level tree is about 8 petabytes. Which means that you rarely have a 3-level tree, right? So just, I mean, I was trying to understand what this is, but the real answer is these trees are 1 or 2 levels deep.
A lot of the time that's
I mean, there are asymptotics, but the asymptotics go out. The file sizes grow so quickly in this that once you get to about a 4 or 5 level tree, it's bigger than the total amount of disk space produced ever in the history of the world. No, really, right? Powers of 125 grow times 4 megabytes grow quickly.
So, it's actually about twice that. The implementation we use actually has a fan out of average of about 10, not 125. So the tree is going to be about twice as.
You have a lot of data in this show. What did you put in there?
Well, this was engineered for variable size keys, so you don't really know how big the keys are. And so if I'd have to go talk to the people who built it.
Keys are file offsets.
Keys are actually, well, wait for it. Let me tell you about our file system.
Okay.
Keys are not just file offset.
So for the queries, you assume what synchronous feedback. A query completes and you do a new query.
Yeah.
And can you change the computation model to do queries in batches and get different models? If you do asynchronous reply when queries.
So I think, so I haven't thought about that. I believe there are some lower bounds on batch query processing in external memory. And they are not very optimistic lower bounds. As in, once your data is large enough, you can't do batch queries much faster than simply doing each of the queries one at a time. But I'd have to, don't take that with, as gospel. Let me tell you about the file system. Hopefully we'll have enough time to actually get to the file system here. But the point here with these numbers is that if we want to build a file system that's going to get this performance, we need to avoid queries and do blind inserts whenever possible. And so here is our schema for implementing a file system. We maintain 2 B the epsilon trees, one of which we call the metadata index and one of which is the data index. And our keys in the metadata index are actually full paths. And the reason we use full paths is that means that files that are within the same directory will be logically adjacent to each other in the database. And so if you want to do a recursive directory traversal, that can be done at the speed of disk bandwidth. So full paths map to struct, stat information, who owns it, how big it is, stuff like that. The data index maps full paths and a block offset to the data. And we use full paths here again. So this file system does not have any notion of an inode. And so it's a radical departure from normal file system design. And what we get for this is we get very fast directory scans. And since these are sorted by the block number, data blocks will be laid out sequentially on disk, more or less. They'll be with a node, and then every so often you have to jump to another node. Rename, we're working on. Yes, but rename is the downside of this.
Rename is always the problem.
Yeah. Here's a quick roundup of how the operations get mapped from file system operations to the epsilon tree operations. A read is a range query, a write can become an upsert, reader is a range query. So we could do very fast, since metadata just can become an upsert. So for example, in Linux, there's this thing called A-time on a file that they often turn off updating that. Basically, every time you access a file, it has to update that thing on disk.
Yeah, we did that too.
Yeah, such an idiotic design. I love this rant that you can read on Wikipedia about. The POSIX designer said, let's turn every read into a write. Yeah, so, but hey, now we can actually do it. We can do efficient directory scans. These operations, unlink and rename, as you've already seen, don't map nicely to the operations I've told you about so far. And so those are a problem right now. In the interest of time, I'm going to skip the details on this. The high-level point is that upserts enable you to write new data to disk very, very fast. And so imagine an application does a small, like a 1-byte write into the middle of a page. It's cached, and that page cache is clean. Now, normally what the OS would do is it would write that byte to the in-memory cache, mark it dirty, and then later on write 4 kilobytes of data back to disk. What we can do is we just write the byte back to disk. We apply the byte to the in-memory cache, and we say it's still clean. And so that avoids write amplification, where a small write gets amplified into a big write. If the page wasn't cached at all, we can also avoid having to read the page in. And so this is one of the cool aspects of how write optimization can actually change what the right decision is in the design of your system, whether you should do write back or write through caching. Here's the architecture of the system. We basically took B to the epsilon tree implementation, and it's just imported it as a binary blob into the kernel. This is our VFS API that translates from file system operations to B epsilon tree operations. This code was user space code, so it expects a file system. So we wrote a shim layer, and then it just uses ext4 underneath. So the ext4 is doing our block management on the disk for us. This code it's really kind of amazing. This is C++ code, which in Linux is verboten. And so we just compile it in user land and then just shove it in there and hope for the best, and it actually works great. Now let me tell you about performance results. So here's where we get to where the rubber meets the road. Did we actually get a speed up for random writes? That was one of the things we started out with. How do we do on sequential I/O? We wanted to not sacrifice that. And do we actually see a speed up in any real world application? We tested it on a computer. That computer had a disk. We're going to compare it.
That computer had a really tiny disk.
Yeah.
Okay.
But we didn't do large experiments. We just did.
Obviously not. A really tiny disk.
We're going to compare against several other common file systems. All the tests start with a cold cache, and all the tests end with sync operations to make sure that everything's actually on disk. No cheating there. Here is the time it took us to do 1,000 random 4-byte writes into a 1 gigabyte file on the different file systems. This is BetrFS time, so lower is better. Log scale. If you work it out, if you want to know what the actual numbers are, it's about over 50 times faster. So this is a huge improvement in random write performance by using WriteOptimized data structure, which is what you expect. That's their bread and butter. This is showing the benefit of being able to do these blind writes. Small file creation is also basically a small write operation. So creating a new file, you have to update a little bit of metadata, then we write 200 bytes of the file. They're balanced in the directory, so you don't hit any dumb file systems, worst case, where it's just using a linked list for its directory data structure or something like that. And what this graph is showing is the instantaneous creation rate for new files, again, on a log scale. And this is after it's created yay many files. And so you can see BetrFS is creating like 10,000 files per second, where other file systems have dropped down to 1,000 or maybe even somewhere in the range of 100 files per second. But again, this is the kind of bread and butter application for a write-optimized data structure.
Why does ZFS get better?
ZFS is weird. ZFS, I don't know. I guess maybe it's warming up its cache or something. How are we doing on time? Are we?
You're okay.
Okay. Oh, we're okay. All right. Again, this is a log scale. Sequential I/O. Here we don't win. We're reading a gigabyte file about 40 kilobytes at a time. Our read performance is within the ballpark of a normal file system, and probably with some optimization we can get that. We can close that gap. Our sequential write performance is actually about half or a third of the most file systems performance. Now, one reason could be that we're writing all the data twice, because our beta epsilon tree implementation does full data logging, whereas these other file systems are not doing full data logging, except for ZFS, which I understand the students tell me is doing logging in triplicate. It literally writes all the data 3 times. So we're actually working on this. We have some tricks where we're going to preserve the semantics of full data journaling, but we're not going to have the costs. We're going to write the data one time. But that's still ongoing work. Here is our delete performance in the version of BetrFS that was described in the FAST paper. So as the file gets bigger, the time to delete gets bigger. Yeah.
Since you don't have inodes, why don't you implement rename or delete just by having another path to path with the epsilon tree to remember what you deleted and what you renamed?
So basically have a pointer like a symbolic link.
Yes.
Degeneracies when you have long chains of those links. If you rename it A to B and B to C and C to D, then
Right.
we don't want to have those degeneracies.
But you can merge those things, right?
Yes. But then what happens if I rename a full directory and then something down inside that directory? I didn't think it through, but we have some other plans for doing that. We have fixed the delete performance by implementing essentially an upsert that applies to a range of messages. It says delete all these messages. So now this is our performance. I think we're actually faster than most other file systems that deletes now. So the old scaling was terrible. The new scaling is good. Does it actually benefit any real application? Did we get the speed up that we wanted for recursive directory scans? So here we're doing a find, which is only looking a recursive traversal of metadata. Here we're doing a grep, which is a recursive traversal of data. And here's time, and here's BetrFS on the find, and here's BetrFS on the grep. So this is a pretty dramatic speed up for these kinds of benchmarks. Now you might say find and grep are artificial, but you might think about things like a backup or a virus scan on a computer. These are real workloads that people care about.
So this is a file system with small files, right?
This was the Linux source code.
Lots of small files. Okay.
Yeah. And this is because our sorting method, our way of organizing the data, puts directories and their contents close together. Some real benchmarks. Here's an IMAP server, and it's doing a bunch of message reads and message marking. I don't actually know the benchmark in detail. Here's the time to run the benchmark, and as you can see, we do quite a bit better than other file systems. But we're no longer in log scale territory. So the only one that outperforms us is ZFS, which we have to look into how it does that. If you rsync code between 2 directories on the same file system, so this is rsyncing between a BetrFS and a BetrFS directory, this is rsyncing between a ButterFS and a ButterFS directory, then the megabytes per second that we achieve is quite a bit higher than other file systems. And that's presumably because we had to do rsync with the -- in place flag. Otherwise, it actually makes a temporary file and then renames it, which, as you already pointed out, is we're not going to do well on. So we cheated a little. But if you do that, then it can basically issue blind writes to create the new files and blind writes to write the new data into the files. And so it can run really fast. So sort of in summary, did we achieve our goals? Sequential I/O, random I/O, I would say it's pretty much a slam dunk. I'm really proud of that performance. Sequential I/O, we've got work to do, but we have work in the pipeline. And yes, there are real world applications that benefit from this kind of performance. Okay, so wrapping up, the big picture message for our work is that we believe that it is possible to have your cake and eat it too. You can have a file system that supports good random I/O and good sequential reading of that data back. So you don't have to make this trade-off that you're sort of forced to between something like ext4, which is good sequential reads but not good on random I/O, or something like a log structured file system, which is good for random writes but not so good at sequential reads. But write optimization so dramatically changes the performance landscape of the underlying data structures that we need to revisit design decisions that we've made in the past. We abandon inodes and organize the data quite differently. We use write-through caching instead of write-back caching because writing is so cheap now. And we engineered the system to perform blind writes whenever possible. So we think there's a lot of research opportunity here to figure out other ways that these new data structures can impact system design and the way they can be used to speed things up. And it's open source. All right, thank you. Yeah.
It seems like a lot of the benefits of this just come from the blind write optimization, which could be done without the write optimization. You could use blind writes, have a log of blind writes on any file system, and maybe that would be a good way to get your ideas into mainstream file systems as one step at a time.
So that's actually an interesting point. So your idea would be maybe we would blindly write stuff into a log or into a buffer in memory?
Yeah, and then a log on disk and to keep it in the buffer in memory, right?
Yeah. So one thing I can point to is there is a database that does something like this, InnoDB, which is the database storage engine for MySQL, the default one. It has what's called an insert buffer. And so as data is being inserted into an index, it's just being stored in memory. And then when that buffer becomes full, it tries to pick some part of the data that will that is all going to the same place on disk and just flush it all the way to a leaf. So it just inserts it into a Btree. Standard Btree is the on-disk data structure. And this gets a speed up. It's actually, InnoDB is a really good Btree. So it gets you maybe a 3 or 5x speed up. But it doesn't get you a 30 or 100x speed up in that scenario setting. Now maybe we can adapt it or do something a little bit different in file systems. So, yeah.
So I hear that disks are on their way out.
Yeah.
And there's this new thing called Flash that's coming in. How does all this change in a Flash world?
So so some of my collaborators have benchmarked this on Flash. Martin at Rutgers is doing that. And there's 2 comments I would say about Flash. One, I haven't seen the benchmark results. One is, since this does writes in big chunks, like 4 megabytes, it's actually much kinder to your Flash in terms of erase cycles and having to go do garbage collection and what all that work the Flash translation layer has to do. The other thing I would say is, although I don't know the file system benchmark results, I have seen benchmark results of a database built on the same Btrees epsilon tree backend on Flash, and it dramatically outperforms a Btree on the same Flash disk. So even though Flash doesn't have the big seek time, there's still setup costs, and so you can get a win out of doing this. Now, the next question you should ask is, well, what about non-volatile RAM? Aren't we all just going to have our file systems and everything in RAM? And there I don't have a good answer for you. That might be a disruptive technology for us.
Yeah, but we stopped believing those, so it doesn't matter.
Oh, really?
Well, yeah, we've been waiting for phase change memory now forever, and memristors are phase change memory plus 10 years. So there's the battery-backed set of technologies and a lot of things that don't seem to work.
Yeah.
Any other questions?